Welcome to the lesson on properties and types of metals. By the end of this lesson, you will be able to explain the importance of metals used in aircraft structures and understand why proper material selection is critical for safety and reliability. You will identify the different forces that act on aircraft materials during flight. You will also describe the important physical and mechanical properties of metals such as strength, hardness, ductility, and toughness. In addition, you will distinguish between ferrous and non-ferrous metals and understand how aluminum alloys are classified using the 4-digit numbering system and temper designations. Finally, you will identify common aircraft metals and their applications and understand the key requirements that must be met when substituting aircraft metals during maintenance or repair. Let us first understand why aircraft metals are so important in aviation maintenance. Aircraft structures are built using carefully selected structural metals that provide the required strength while keeping the aircraft lightweight. Each metal used in an aircraft has specific properties such as strength, durability, corrosion resistance, and weight. These properties determine where the material can be used safely in the aircraft structure. Even a small deviation from the original design specification or the use of an incorrect material can compromise structural integrity. When unsuitable materials are used, the aircraft structure may weaken and lead to serious failures. Because of this, proper material selection is one of the critical responsibilities of aircraft maintenance technicians. Understanding different metals and their properties allows technicians to perform safe repairs and maintain the reliability of the aircraft. Before discussing metal properties, it is important to understand the forces that act on aircraft structures during operation. Aircraft components are constantly subjected to several types of mechanical forces while the aircraft is in flight or during ground operations. Compression is a pushing force that shortens or compresses a material. For example, compression occurs in structural members that support weight. Tension is the opposite type of force. It is a pulling force that stretches a material. Aircraft cables and structural members often experience tension loads. Bending occurs when a component curves because one side is in tension while the opposite side is in compression. Torsion is a twisting force acting along the length of a component, such as in rotating shafts. Shear occurs when two connected surfaces slide past each other. Understanding these forces helps technicians understand why materials must possess certain strength and structural properties. The next step is to examine the properties that allow metals to resist those forces. Metals used in aircraft must possess specific physical and mechanical properties to perform safely under operational loads. Some of the most important properties include hardness, strength, and density. Other important properties include malleability and ductility, elasticity, toughness, brittleness, fusibility, conductivity, and thermal expansion. In the next slides, each of these properties will be explained in more detail. Now let us begin examining the individual properties of metals, starting with hardness and strength. Hardness refers to a material's ability to resist abrasion, scratching, cutting, or penetration. This property is important because aircraft components are often exposed to friction, wear, and surface damage during operation. Hardness can be increased through manufacturing processes such as cold working or heat treatment. This is commonly done with steels and certain aluminum alloys to improve their resistance to wear and deformation. Strength is another critical property. It refers to the ability of a material to resist applied stress without experiencing permanent deformation or failure. Materials used in aircraft structures must have sufficient strength to withstand the loads produced during flight, turbulence, landing, and other operating conditions. Density refers to the weight of a material per unit volume. In aircraft design, density is extremely important because heavier materials increase the overall weight of the aircraft. An increase in aircraft weight directly affects fuel consumption, performance, and payload capacity. Therefore, lightweight materials with adequate strength are preferred in aircraft construction. Malleability describes a material's ability to be rolled, hammered, or pressed into thin sheets without cracking or breaking. This property is particularly important for metals used in aircraft skin and structural panels. Materials with good malleability can be shaped and formed into complex aircraft components while maintaining structural integrity. Another important group of metal properties includes ductility and elasticity. Ductility refers to a material's ability to be drawn into wire or stretched without breaking. This property is important in applications such as electrical wiring, cables, and certain structural components. Materials with high ductility can undergo significant deformation before failure, which often provides an early warning before a structural component breaks. Elasticity refers to the ability of a material to return to its original shape after the applied force is removed. Many aircraft components rely on this property to maintain structural integrity under repeated loads. However, if the elastic limit of the material is exceeded, permanent deformation occurs and the material will not return to its original shape. Toughness refers to the ability of a material to absorb energy and resist tearing, cracking, or breaking when subjected to stress. Materials with high toughness can withstand impacts and sudden loads without failing. This property is important for aircraft components that experience dynamic loads, such as landing gear and structural supports. Brittleness is essentially the opposite characteristic. A brittle material tends to fracture suddenly with little or no deformation when subjected to stress. A common example is glass, which shatters when dropped. In aircraft structures, brittle materials are generally undesirable because they can fail suddenly without warning. The final group of metal properties includes fusibility, conductivity, and thermal expansion. Fusibility refers to the ability of a material to melt and fuse with another material when heated. This property is important in processes such as welding, brazing, and soldering. Different metals melt at different temperatures. For example, steel melts at approximately 2600 degrees Fahrenheit, while aluminum melts at approximately 1100 degrees Fahrenheit. Conductivity refers to the ability of a material to conduct heat or electricity. Metals such as copper are widely used in aircraft electrical wiring because of their excellent electrical conductivity. Thermal expansion refers to the tendency of a material to expand when heated and contract when cooled. This property must be considered when designing and maintaining aircraft components that operate under varying temperature conditions. Now that we understand the properties of metals, the next concept to understand is alloys. Pure metals often do not possess the strength, durability, or erosion resistance required for aircraft applications. For this reason, base metals such as iron are commonly combined with other metals or elements to improve their physical and chemical properties. When a base metal is combined with other elements, the resulting material is called an alloy. Alloys allow engineers to tailor the properties of a metal to meet specific performance requirements. Aircraft alloys are generally classified into two major categories: ferrous alloys and non-ferrous alloys. Ferrous alloys contain iron as the primary element, while non-ferrous alloys contain little or no iron. Let us now look more closely at ferrous metals. Ferrous metals are metals that contain iron as their primary element. These metals are commonly used in aircraft components that require high strength and durability. Typical alloying elements added to iron include carbon, nickel, and chromium. Carbon is one of the most important alloying elements in steel. When carbon is added to iron, usually up to about 1% in many steels, it significantly increases the strength and hardness of the material compared to pure iron. Because of their strength and toughness, ferrous alloys are commonly used in high-stress aircraft components such as landing gear parts, fasteners, and engine components. In addition to understanding the composition of ferrous metals, it is also important to understand how these alloys are identified. Many steel alloys are identified using a 4 or 5-digit numbering system. These identification systems were developed by the Society of Automotive Engineers, commonly known as SAE, and the American Iron and Steel Institute, or AISI. The numbers assigned to each alloy indicate the type of alloy and its chemical composition. By understanding these numbering systems, technicians can quickly identify the type of steel being used and determine whether it is suitable for a particular aircraft application. After discussing ferrous metals, the next category to examine is non-ferrous metals. Non-ferrous metals are metals that do not contain iron as their principal element. These metals are widely used in aircraft because many of them provide excellent strength while remaining relatively light weight. Common examples of non-ferrous metals used in aircraft include aluminum, titanium, copper and copper alloys, magnesium, Monel, and Babbitt. Each of these materials offers different advantages. For example, aluminum provides an excellent balance of strength and low weight. Titanium offers exceptional strength and corrosion resistance, and copper is widely used for electrical conductivity. Among all aircraft metals, aluminum is one of the most widely used materials in modern aircraft construction. Aluminum offers an excellent combination of lightweight, corrosion resistance, and adequate strength. Commercially pure aluminum has a tensile strength of approximately 13,000 pounds per square inch. However, by adding alloying elements and applying heat treatment, the strength of aluminum alloys can increase to about 65,000 pounds per square inch or more. Aluminum, used in aircraft structures, is generally classified into two forms: cast aluminum and wrought aluminum. Each form is produced using different manufacturing processes and is used for different types of aircraft components. Now let us compare the two major forms of aluminum used in aircraft construction: cast aluminum and wrought aluminum. Cast aluminum alloys are produced by pouring molten aluminum into molds. This process allows manufacturers to produce complex shapes and components that would be difficult to create through other manufacturing methods. Cast aluminum alloys are classified into two groups: heat-treatable and non-heat-treatable alloys. Wrought aluminum alloys, on the other hand, are produced by mechanical processes such as rolling, forging, extruding, or drawing. Wrought aluminum is the most commonly used form of aluminum in aircraft structures. Like cast alloys, wrought alloys are also classified into heat-treatable and non-heat-treatable categories. To properly identify aluminum alloys, engineers and technicians use a 4-digit alloy designation system. This system is used primarily for wrought aluminum alloys and helps identify the primary alloying elements present in the metal. The first digit in the alloy number indicates the major alloying element in the series. For example, the 1000 series represents nearly pure aluminum, while other series contain alloying elements such as copper, manganese, silicon, magnesium, or zinc. Now let us look more closely at how the aluminum alloy numbering system works. In aluminum alloys, the first digit, typically between 2 and 8, indicates the major alloying element present in the alloy series. The second digit indicates whether modifications have been made to the original alloy composition. The third and fourth digits identify the specific alloy within that particular series. The 1000 series aluminum alloys follow a slightly different rule compared to other alloy groups. In this series, the last two digits indicate the percentage of aluminum purity above 99%. For example, aluminum alloy 1100 contains approximately 99% pure aluminum. Alloy 1130 contains approximately 99.3% aluminum, and alloy 1175 contains approximately 99.75% aluminum. These alloys are known for their excellent corrosion resistance and workability, although they generally have lower strength compared to other aluminum alloy series. Let us examine a specific example, alloy 2117. The first digit 2 indicates that copper is the primary alloying element in this series. The second digit 1 indicates a modification to the original alloy composition. The final two digits, 17, identify the specific alloy within the 2000 series. By understanding how to interpret these numbers, aircraft maintenance technicians can quickly identify aluminum alloys and determine whether they are appropriate for a particular aircraft repair or structural application. In addition to the alloy number, aluminum alloys also include a temper designation that indicates the heat treatment or strain hardening condition of the metal. The temper designation always follows the alloy number and is separated by a dash. For example, in the designation 2024 T3, the number 2024 identifies the aluminum alloy, while T3 indicates the temper condition. In this case, the T3 temper means the alloy has been solution heat treated, cold worked, and naturally aged. These processes significantly improve the strength and mechanical properties of the material. Different letters are used to represent different temper conditions of aluminum alloys. The letter F indicates the material is in the as fabricated condition. The letter O indicates the metal has been annealed and recrystallized, which softens the material and improves formability. The letter H represents strain-hardened alloys. Variations such as H1, H2, and H3 indicate different levels of strain hardening and stabilization. The letter W indicates the alloy has been solution heat treated but is in an unstable condition. Finally, the letter T indicates the alloy has been heat treated to produce stable temper conditions that improve strength and durability. Let's look at other non-ferrous metals and their alloys. An important group of aircraft materials includes magnesium and its alloys. Magnesium is the lightest structural metal used in aircraft construction. Because of its extremely low weight, it is commonly used in components where weight reduction is critical. Magnesium is often alloyed with elements such as aluminum, zinc, or manganese to improve its strength and mechanical properties. Large aircraft may contain more than 2,000 pounds of magnesium components. However, magnesium also has some disadvantages. It is highly reactive, prone to corrosion, and can present a fire hazard. For this reason, fires involving magnesium must be extinguished using a Class D fire extinguisher. Titanium and its alloys are also widely used in modern aircraft structures. Titanium is highly resistant to corrosion and can withstand high temperatures, making it suitable for components exposed to extreme operating environments. Common applications include engine components, fasteners, and structural parts that require high strength and corrosion resistance. Titanium alloys are generally classified into three categories: alpha alloys, beta alloys, and alpha-beta alloys. Each classification offers different combinations of strength, weldability, and temperature performance depending on the aircraft application. Copper and its alloys are another important group of non-ferrous metals used in aircraft. Copper has excellent electrical and thermal conductivity, which makes it especially valuable in aircraft electrical systems. For this reason, copper is commonly used in electrical wiring and various electrical components. Two common copper alloys used in aircraft are brass and bronze. Brass is an alloy of copper and zinc, sometimes containing small amounts of additional elements. Bronze is an alloy of copper and tin. These alloys provide improved strength and corrosion resistance compared to pure copper. Nickel alloys are also used in aircraft applications that require high strength and resistance to harsh environments. One example is Monel, which is a high nickel alloy known for its strength and excellent resistance to corrosion. K-Mono is a related alloy containing nickel, copper, aluminum, and titanium. This alloy is non-magnetic and can be heat treated to improve its strength. Another important nickel alloy is Inconel, which is commonly used in high-temperature aircraft engine components because it retains its strength and stability even under extreme heat conditions. Finally, when replacing and repairing aircraft components, it is sometimes necessary to substitute one metal for another. However, strict requirements must be followed to ensure that the substitution does not compromise aircraft safety or performance. First, the replacement material must maintain the original structural strength of the component. Second, the original contour of the part must be preserved so that aerodynamic smoothness is not affected. Third, the replacement material must match the original weight to maintain proper aircraft balance and performance. Finally, the replacement metal must provide equivalent corrosion resistance to ensure durability and long-term service life. Let us now summarize what we have learned in this lesson. Aircraft structures rely on carefully selected metals that provide the necessary strength, durability, and reliability required for safe operation. Aircraft materials experience several types of structural forces, including tension, compression, shear, bending, and torsion during flight. Metals are defined by important physical and mechanical properties such as strength, hardness, ductility, elasticity, and toughness. Alloys are formed by combining base metals with other elements to improve their properties and performance. Aircraft metals are generally classified into ferrous metals that contain iron and non-ferrous metals that do not contain iron as the primary element. Aluminum alloys are widely used in aircraft construction and are identified using a 4-digit alloy designation system, along with tempered designations that describe their heat treatment condition. Common aircraft metals include aluminum, magnesium, titanium, copper alloys, and nickel alloys. When substituting aircraft metals during maintenance, it is essential to maintain the original strength, contour, weight, and corrosion resistance of the component. Thank you for your attention.